In this module, I will review local atmospheric stability, which is an important concept for air pollution transport. Atmospheric stability is defined as the tendency of an atmosphere to resist or enhance vertical motion. It is determined by the magnitude of the ambient lapse rate compared to the adiabatic lapse rate, which is given the symbol gamma. So the question is, how are these related? We'll go ahead and define both terms. The adiabatic lapse rate is the rate at which air cools as it rises and expands, or heats as it sinks and compresses. Due to the high heat capacity of water, the ambient lapse rate is strongly dependent on the humidity of the air. For us, we will always work with the dry air condition, so the dry adiabatic lapse rate. Dry air with no humidity loses temperature -9.8 degrees Celsius per kilometer. And we say that it loses temperature because as you move 1 kilometer in the atmosphere, air cools. You can compare that to moist air, which loses heat much slower, at around 6 degrees Celsius per kilometer. For us, we will work with different units. We'll work with units of -1 degree Celsius per 100 meters, which is equal to around -9.8 degrees Celsius per kilometer. But this is the condition that you need to remember. So this is the dry adiabatic lapse rate, which is going to be constant for all conditions. And what we will do is compare that to the ambient condition. The ambient lapse rate is also called the environmental lapse rate. It refers to the actual temperature gradient that exists with height. The reason why stability of the atmosphere is important is the transport of a smoke trail or a plume from a pollution source is dependent on the stability of the atmosphere. I'll walk you through the picture from your textbook that demonstrates this. Here I'm showing you the graph for the stability, which is referred to as neutral or adiabatic. In this picture, you have a dry parcel of air, which we can pretend comes from this smokestack. And so this dry parcel of air here is going to lose or gain temperature according to the dry adiabatic lapse rate of -1 degree Celsius per 100 meters. And that's what you'll see as this dry parcel of air moves up into the atmosphere, it loses 1 degree Celsius for every 100 meter. Likewise, as it moves down 100 meters, it gains 1 degree Celsius. Now we'll compare that to the ambient condition, which is shown here in the adjacent atmosphere. In this situation, the ambient temperature loses temperature at the same rate as the dry adiabatic condition. So in this case, the ambient condition loses temperature at -1 degree Celsius per 100 meters, which is equal to the dry adiabatic condition. In this case, we would say that the atmosphere is neutral. What this means is that this dry parcel of air is the exact same temperature, 20.15, as the adjacent atmosphere. And so relative to the adjacent atmosphere, it has equal probability of moving up or down into its surroundings. The next condition is referred to as unstable. And although the word unstable has a negative connotation, this is the most desired condition for pollution dispersion. With pollution dispersion comes dilution. Again, we'll see that we have a dry parcel of air, which is going to lose or gain temperature by 1 degree Celsius every 100 meters. But we'll compare it to the ambient condition. And in this case, the ambient condition is losing temperature, defined as delta T divided by delta Z, by 1.25 degrees every 100 meters. So 100 meters up into the atmosphere, the ambient condition is 19.9 degrees Celsius versus 20.15 degrees Celsius. The dry parcel of air is warmer than the surrounding or adjacent atmosphere, and so it will rise relative to the adjacent atmosphere. Likewise, if the parcel of air sinks initially, it will be cooler than the adjacent atmosphere. So we're comparing these, and cool air sinks. And so as this parcel of air moves in the direction X from the smokestack, it will both rise and sink. And so the dispersion is great here, and so is the dilution. And the rule of thumb here is that the ambient lapse rate is less than the dry adiabatic. So in this example, negative 1.25 degrees Celsius per 100 meters is less than negative 1 degree Celsius per 100 meters. The last case of stability is a stable atmosphere. This is the stability class when isotherms and inversions occur. Both of these situations prevent the dispersion of pollution and result in high concentrations near the ground surface. So this poses the greatest public health risk. Returning to our figure here from your textbook, your dry parcel of air loses temperature by 1 degree Celsius every 100 meters. So the ambient lapse rate is only negative 0.5 degrees Celsius per 100 meters. The result is that the ambient air is 20.6 degrees Celsius and your dry parcel of air is 20.1 degrees Celsius. So the ambient air is warmer and your dry air is cooler. So your parcel of air is going to sink relative to the ambient or surrounding atmosphere. Likewise, if this dry parcel of air initially sinks, it will gain temperature much faster than the ambient atmosphere. And so 100 meters down, it is now 22 degrees Celsius and your ambient condition is 21. This air is now relatively warmer and it will rise. The result here is that you get a concentrated plume of dry air that stays in the atmosphere close to the surface. A stable atmosphere is the most concerning. The rule of thumb here to determine a stable atmosphere is that the ambient lapse rate is greater than the dry adiabatic lapse rate. So in this case, we had negative 5 degrees Celsius per 100 meters is greater than negative 1 degree Celsius per 100 meters. You include the sign when you take the comparison. In your homework, you're given actual weather tower data, and you're asked to determine the stability class. As an example, you could be given 2 different heights in the atmosphere and temperatures. So in this example, I'll say that a weather tower is measuring temperature at 2 meters in the atmosphere and 318 meters. At 2 meters, the temperature is negative 2 degrees Celsius, and at 318 meters, it's negative 6.21 degrees Celsius. We'll simply take the delta T divided by the delta Z, and we'll get negative 6.21 minus negative 2.05 degrees Celsius divided by 318 minus 2 meters. And that yields a number of negative 0.0261 degrees Celsius per meter. We'll multiply the numerator and the denominator by 100 meters in order to get to our desired unit of negative 2.61 degrees Celsius per 100 meters. This condition is less than the dry adiabatic condition of negative 1 degree Celsius per 100 meters. So therefore, we would say that this condition is unstable. If you think about this, you have a condition where your ambient air is losing temperature much faster than the dry adiabatic air. So as that parcel of air, which is dry, rises, it's going to stay relatively warmer than your ambient condition, because your ambient condition is losing temperature faster. It's becoming cooler relative to your warmer parcel of air. The result is that your parcel of air will continue to rise relative to the adjacent atmosphere. This is unstable.